Okay, so okay.
Okay, yeah.
Well, welcome everyone to this afternoon's presentation from the Victorian chapter of IEEE Victoria, Antennas and Propagation and Microwave Theory and Techniques. My name is Les Davey, and I'll be chairing this presentation. Our chairperson, Fatima Babian, is also online, and she'll be operating the Zoom system. And she's already started the recording. Um, a special welcome to our interstate chapter colleagues who are co-hosting this event, which includes the Northern Australia section, New South Wales section, South Australian section, Queensland section, University of Technology, Sydney. The title of today's presentation is Electromagnetic Radiation, explaining how EM radiation leaps off a wire without reference to Maxwell's equations. Our presenter today is Dr. George Galanis, and he's what I would call, or from his uh, biography, you'll see that he's a polymath with many interests. Um, he's a scientist with a career spanning systems engineering, aviation, human factors, operations research, and simulation. He has a Bachelor of Science degree from Monash University and a PhD in engineering from RMIT. He's also an associate in Music Australia from Melbourne University, which was a new one to me. Um, he has been the scientific advisor to the Royal Australian Air Force over the period 2012 to 2015. And I got to know George through amateur radio, and George is a licensed amateur radio operator back since 1976. His call sign is VK3EIP, and his current interest is in portable Earth Moon Earth operation in the 23 centimetre or 1296 megahertz band. And you'll see on the background to George's presentation is a picture of his 3 metre dish. So with that, I'd like to hand over now to George. George's presentation will go for about 45 minutes and then be followed by 10 to 15 minutes of question and answer. So please, if you've got a question, could you put it in the chat, and then we'll go to those questions after George has finished his presentation. So over to you, George.
Thanks, Les. And I have to say it's an honour to be invited in to give a presentation to such a distinguished group. You're all members of the IEEE. So, and as I've said to Les, a lot of you probably will be more qualified than I am about EM radiation. It's more of a hobby to me, and it's part of the amateur radio side of my interest, and I'll talk about that in a minute. So the talk I'm going to give is based on an article, or based on two articles. They broke it up into two bits, published in the Amateur Radio magazine, which is the magazine for the Wireless Institute of Australia, and I've got the reference down here at the bottom. So I'm going to talk about essentially what's in that article. And if you, I'm going to, because you're such a qualified audience, I'm going to skip over a lot of the maths. I won't be going through the algebra in detail. We just won't have the time to do that. And I'm going to assume a knowledge of a few things, not in detail, but just that you're aware of the issues and some of the equations that come out of it. But I'll be assuming that you know something about special relativity, you know to do the algebra involved, and yeah, and if you want more detail in it, you can actually look in the articles, and if you want even more detail on that, you can look in the references, which I'll go over a little bit when was I going to say? The references that'll be a part of the presentation. So the question is, how do we explain EM radiation to a bigger audience? Um, the gold standard explanations for electromagnetic radiation are Maxwell's equations, as I'm sure you all know. The prerequisite for Maxwell's equations is vector calculus, and that really brings us up into the undergrad level, first and second year. First year mathematics in vector calculus, and at least when I did this stuff, I didn't do physics in second year, but that's where Maxwell's equations were taught when I did it, and I'm sure it's at that sort of level still. And that's good for physicists and engineers. But what about everybody else? What do we have? And what I've found in the amateur radio field is we're left with analogies to light. So we say, imagine a radio wave is like a light wave. And this presentation is about trying to find a bridge between the analogy level and the Maxwell's equations level. And I think that's possible, and that's what the talk's about. I was particularly aiming at year 11 and 12 maths and physics. The reason being, well, that's where students can probably do a bit better than an analogy. High school students can do better than an analogy. And it's also the sweet spot for the advanced amateur radio operator level. I think most of the amateur radio operators that are at the more advanced level have got at least high school maths. So I've talked about the presentation. So about the article. The article's actually, I don't have the title here, but the article's called What Happens After We Push the PTT Button. So that was the question in the back of my mind when I was exploring all of this. So just a little bit of what my interest in amateur radio, well, where it's gone anyway. I've held, as Les mentioned, a license since 1974 when I was a teenager. And so for those of you that may not be that familiar with what amateur radio is, I'll just say a few words about that. It's a license that allows individuals to transmit on particular bands, all the way from very low frequency up through into the microwave regions. It's not for profit. And these bands are allocated for people to license people to do their own experimentation for the purpose of self-education. There are international agreements in place for the band allocations, and that's done through the ITU, the International Telecommunications Union. So amateur radio is a worldwide activity. And in Australia, we're licensed by ACMA. Currently, there's 3 levels of license: foundation, standard, and advanced. So advanced is really where I'm pitching this at the 3rd level, the highest level. And like I said, because we're pitching it at the year 11, 12 maths level, it's also potentially of interest to people involved in education in physics and mathematics. So in recent times, when I say recent, since 2015, I've been interested in, I was involved in the CSIRO Scientists in Schools program. And I don't think that program still exists, but I happened to, while I was working in Canberra, have the privilege of having a look at a couple of school excursions to Tidbinbilla. And I saw firsthand how students respond to radio astronomy, particularly with the large systems that Tidbinbilla have, the large dish that they have. And I realised there was a need for an introduction to radio astronomy prior to these excursions. I think the kids would get a lot out of that. So my focus was on developing a portable system to take to schools. And I've got the picture here is of my 3-metre what's called a stress dish. I don't know how familiar you guys are with the different techniques for building dish antennas. But it's called a stress dish because the spokes are straight and you stress them into a curved shape, which is near parabolic. So that's this particular dish here. And I built that mostly for myself at that point in time because I didn't know much about microwaves and dishes. And it was for me to learn about the 21 centimeter band for radio astronomy because that's where you get the hydrogen line, and the 23 centimeter band where I could transmit on. In more recent times, after I came back from Canberra to Melbourne, I set about building something a bit more practical in terms of moving it around. And so I modified this television dish. I think it's C-band, they call it, if I remember right. And I modified this television dish to work on the 23 centimeter band. And I mounted the whole lot on a trailer, and I have actually driven it around, and that works quite well. The setup time's still a bit too long for my liking. The radio equipment's down the back here, and it includes a 500 watt amplifier for the 23 centimeter band. And that does actually get audible echoes just using straight Morse code. So the idea, as I said, the idea behind all of that was to promote STEM in schools. So anyway, that's the aim of it. Now, going back to this talk, when you build these systems, ACMA requires an EMR compliance audit, and this was introduced back in the late 1990s. And to the licensed amateur radio operator, this is all rather new. Before we had these APANSA EMR limits, the limits were stated in terms of power, in particular power into that you're putting into the antenna. And then ACMA introduced these EMR compliance statements into our license conditions. And power density limits sort of make sense to the amateur radio operator because it's sort of related to the power you're putting into the antenna. But the electric and magnetic field limits don't make so much sense, and they haven't actually been taught very well, mainly because they're not the way it applies to amateur radio is not really stated very well in our syllabuses. So what I'm going to talk about in this talk is about the electric field. It's not about the magnetic field at all. I don't really mention that. But the effect of these guidelines was to let amateur radio operators know that they don't know as much about propagation as perhaps they think they do. And the Wireless Institute of Australia is trying to address this over the last few years. And they've introduced just recently education pages on their website. And their particular focus in meeting the ACMA audit requirements is the RSGB calculator. It's the Royal Society of Great Britain, which is the Wireless Institute of Australia's equivalent. And they have pages there for doing audits using a web-based calculator. But that's not really great for teaching the principles, what's actually involved. So that's where my interest in this sort of originates. The trigger for me writing the article was an article that appeared in the Silicon Chip magazine, which comes out of Australia. And the title is, you can't see that very well, but it says The Derivation of Maxwell's Equations. And if you've seen this article, it was published in 2024, you'll see there isn't actually a derivation there. They certainly show us the equations, but they don't derive anything, not really. And it sort of follows the analogy type of explanation that I mentioned before. And you can see here they've got these weather maps, and that's to try and convey the idea of what a grad is and what a curl is. and um, and so it is sort of pitched at that sort of level, and that's quite common. Find for explanations to the non-engineer scientist physicist. Around the time this article came out, I was talking to Roger Harrison, who's the editor of the Amateur Radio magazine. I was talking to him about another article I'd written on dish antennas. And in that article, again, I was already on the path of trying to see if there were explanations that we could use that don't rely on Maxwell's equations. And in that particular article, I used Huygens' concepts of wavelets. So I assume most of you would have come across that in your undergrad physics. And there was no equations, no Maxwell's equations required in that article. But I asked Roger, the editor, if he had read this Silicon Chip magazine article, and he had. And like me, he found it good as a broad introduction, but it was a bit hollow in terms of achieving its stated aims. And I asked him if he'd be interested in something better than the AR magazine article, something better than the Silicon Chip article for the AR magazine. And he said he was interested, and that sort of, well, if I've got an interested audience, I thought, well, I'll write the articles and see if something better is possible and what that would look like. So that was the Christmas break between 2024, 2025. I thought, well, the first step is actually derive Maxwell's equations for myself. As I mentioned before, I'd done in general science degree course in first year, and in my second year I did pure and applied maths and computer science. So I hadn't actually gone through the motions of actually deriving Maxwell's equations, and of course the classic problem that people do is the planar wave problem, and that's what you see here is my initial attempt at that, and that was 30 or 40 pages that I condensed down to 11 pages, which is sort of really summarizing what I'd gone through. And of course, you come up with the solution for the planar wave, and you get the classic solution down here, which gives you velocity in terms of permeability and permittivity, which is, Maxwell's famous solution. And that's really great. Yep, I could tick that off my bucket list. I'd solved Maxwell's equations for a particular situation. And so you show that from the starting premises of electromagnetic phenomenon, by a lot of calculus, you end up with an electromagnetic wave. And could I use this explanation for the average advanced amateur radio operator? No, I don't think so. I think it's too complicated for an article in the magazine. It's probably too complicated for an advanced amateur radio operator, and it's certainly beyond year 11 to 12 high school students. So I was essentially back to square one with a bit more knowledge about how Maxwell's equations work. So the challenge was still there at that point. So I'd solved Maxwell's equations. The mathematics is overly complex for the audience that you're aiming it at. And I went back to my original question. When we press the push to talk button on a transmitter, what do we know about what is going on? And so this is what the view that an amateur radio operator would have. I know when I was 14, I built a transmitter, and these bits you know a lot about. An oscillator, some sort of modulation, a power amplifier, then you drive the power coming out of the amplifier into the transmission line, and you jiggle electrons in the antenna. So how does jiggling, I mean, when I looked at that again, I think, yeah, I push the push to talk button and you jiggle electrons in an antenna. how does that lead to an electromagnetic wave? And started to think through that issue. And I realized that, well, you're jiggling a lot of electrons. Do they even have to be electrons? They can just be charged particles. And in fact, why a lot of charged particles? Just one charged particle. If you jiggle a single charged particle, surely that would give rise to an electromagnetic wave. So the whole process must start at Coulomb's law. This was my thinking anyway. I'm sure you've all you all know more about this than me about what causes it. But it's a bit of a mystery to the amateur radio operator who really focuses on this part here, the electronics. So as I explored Coulomb's law, realized it's really about stationary charges and doesn't say much about what happens when you move the charge. And as I read my undergrad physics textbooks again, going over what they said, I realized that they mentioned electrodynamics, but there's books that are dedicated to that topic. And I hadn't really appreciated the significance of what electrodynamics was about. So I started to read my way through the electrodynamics literature. And as I did, I discovered that my question had actually been answered in the late 1800s and had been answered by this guy, Joseph Lamore. And he wrote a paper in 1987 on the, I've got 1987, 1897. I thought I'd fix that. Anyway, he wrote a paper in 1897. Sorry, I've got the wrong date there. And it described the derivation of the power in an electromagnetic emission from an accelerated electric charge. And he was particularly interested in the orbit of an electron and how the acceleration in the electron gives rise to an electromagnetic emission. And one of the things I'm going to so that's a reference there to his actual paper. But yeah, there you go. It's got the right date there now. What we have to remember is he did all this before Einstein's relativity in 1905. And the reason I mention this is because Lamore actually started from Maxwell's equations, at least some of them. But when you look in the textbooks and if you look on the internet to find his derivations, they generally show you the modern version of it, which is not the version he did. And the modern version includes special relativity. And that caught me out. And I'll show you how it caught me out. So his derivation usually starts with a situation something like this. And what I'm going to talk about is based on these guys here, Edward Purcell and David Morin, and they wrote a book, Electricity and Magnetism. And I'm going to talk about essentially the third edition, 1985, because there's a PDF of that accessible on the internet. If you've got access to the later versions, that's great. But for the purpose of the article that I wrote, I was aiming for people that could an edition that they could access as well if they wanted to read more about it. But usually, there's some modifications I have to the way Purcell and Morin approach the problem. They start with a moving charge, a charge that's moving up the z-axis and runs into an obstacle and stops. And I do it the other way around. I have a stationary charge and we give it a kick, an acceleration, to see what happens after it's finished its acceleration. You can do it the way they did it, but then you have to have a concept of where the charge would have been if it hadn't stopped. And that's the bit that caught me out in reading their book and looking on the internet for an explanation of the way Lamore derived his equation. So that's the initial conditions. Then if you give the charge a kick, and there's a reason why we put the charge down here, it's because after we give it the acceleration, We want the acceleration ceases when the charged particle hits the origin, hits zero, and the acceleration at this point stops, and the charge then coasts off at a velocity v. Now, I'm going to show some maths, but I'm not going to go into detail in the maths because we're going to run out of time. But essentially, the kick puts a kink in the electric field. That's the key point. And then after some time, we end up with a situation. Well, at least when I did my derivation, thinking that Lamore preceded special relativity, I show the particle going up the z-axis, and by the time the kink hits the observer over here on the x-axis, the charge is up here. And as we'll see, that's not actually the situation, because if you follow this thinking here, as I did it in a way similar to what Purcell and Morin did, derived the kinematics in the way they did, and you have the electric field in the x direction given by Coulomb's law, which is the same way Purcell and Morin do it, but you end up with a transverse electric field, which actually is you get this equation here, if you do it that way, and the tau divided by c term and the squared are not part of Lamore's finding, in his equation. And so that's if you do it and you don't take relativity into account. And that had me troubled for a while, for a few days actually. I was sort of puzzled over why I was getting an equation different than Purcell and Morin. And in the end, I had to go back to the reference and read the Purcell and Morin very carefully. And relativity is part of their consideration. So I said that's the modern derivation, not the way Lamore did it. His approach is actually, it does include Maxwell's equations. So we need to remind ourselves a bit of what does relativity do to the moving charge. And so this is a typical construction of relativity, of Einstein's relativity. The charge I've put in the prime axes here is x prime and z prime, and the observer is stationary relative to the observer frame, or the laboratory frame, which is the axes without the primes. And you have Lorentz equations over here, which define the connection between the two axes systems. So the important aspect that comes out of that is, well, in the charges frame, in the prime axes, it's purely defined by the Coulomb's law. So we end up with a spherical electric field around the charge. But in the observer frame, it's not spherical anymore. And the reason for that, and the way Purcell and Morin describe it, is if you had a whole bunch of charges on a sheet, and the sheet moved up the z-axis, the Lorentz transformations say the sheet would appear compressed in the observer's frame, or in the laboratory frame. And so if you compress the sheet, you increase the electric field density in the x-axis, and so the Lorentz transformation gives you this increase here. And if you put the increased electric field into the equation for the electric field in the x direction, you end up with this equation, and in the z direction you have this equation here. And if you take the ratio of the two equations of the electric field components, you get this equation here, and then you get tan theta, which is the angle here, and it's purely dependent on the components of the electric field in the z and the x direction. So now, why is that important? Well, um, Purcell and Moran in their book, and this surprised me when I sort of read it closely, they say, let that sink in. Let that sink in. And at first, it was a bit troubling to me. What am I letting sink in? But I've got in the, if you look at my article in the Amateur Radio magazine, you'll see me use a thought experiment where we put ourselves into the future. Humanity is a distant galactic federation, so it's sort of an Asimov type scenario. And we're able to construct a laboratory that's a cube and it's 1 light year on each side. And we put our electric field measuring equipment on this side of the lab, and on the far side we set up an electric charge, huge one, because it's 1 light year away, and we have it down here and we give it a kick, and up it goes, and we note when does it cross the origin, the middle of the far wall of the far part of the lab, and where is our electric field equipment pointing? Well, it's pointing straight at where the charge is, assuming it's moving at a constant speed v. So it's not pointing 1 light year below. It's pointing directly at the origin. And I've got to say that really troubled me because at that point in time, I sort of believed the speed of light was a universal speed limit. And that's sort of the fast, how can you have information traveling faster than the speed of light to show you an instantaneous location of a moving charge? But that is really, really important for the derivation of the of Lamore's equation. And I did a bit of reading, and I discovered Feynman in his lecture series had mentioned something about this because he and Heaviside uh, derived a more general formula for the electric field, moving electric field of a moving charge, moving in an arbitrary path. And Feynman puts it in a way, he says that there's some sort of innate ability for the universe to predict, to enable a prediction of where a particle will be located as close as possible to where it actually is. So he saw this as a sort of a strange part of the way the universe operates. So what does all this have to do with Lamore? Well, if you look at the way, I mean, once you've got that sort of insight, then you look at this problem of deriving Lamore's equation a little bit differently. And the way Purcell and Moran do it is they talk about these two regions, region 1 and region 2. And as I said here, caution not to scale. And in here is the shell that contains the disturbance from accelerating the charge, which is from here. And so the particle has moved up some distance, and out here the disturbance shell hasn't reached the observer yet. So in this region 1, the observer sees the electric field as being from down there, but where the shell has gone past some other observer that might be in region 2, we don't have a sloping line as we had before. Now we've got a straight line going straight out. So I've shown that here as AB. And because we've put the observer out a long way, I haven't stated the assumptions here very well, but the rays are parallel to the axes. And so you get this line there. Any observer in region 2 would see the particle as being where it actually is. And so then you say, well, what happens between each side of this shell? And I think it's Gauss's law that says you can't have a discontinuity in the electric field. And so the electric fields must connect up between C and D and A and B. And so the slope that's of interest to us is this line BC. So again, I haven't gone into detail in the mathematics for the sake of time, but um, uh, it's explained in the article and it's here as well, so you can follow it at your own leisure. So how do we find BC? Well, the line BC, that's pretty straightforward. It's similar triangles between. So we know what EX is. That's given by Coulomb's law. And if once we know the slope of the line BC, which you can work out from the geometry, you can actually find what EZ is, which is the transverse electric field that's generated by the acceleration. So you end up with this equation here, which is the correct form that comes out of Lamore's derivation. And we've done it using a bit of special relativity, which is a little bit simpler than you'd have to go through for doing it Lamore's way. Now, there's a few things that sort of took me by surprise, even though I spent a lot of time in the radio field. I didn't realize that the electric field is an inverse law. So down here we've got xt, which is the distance from the origin, and it's not squared. Yet up here in the direction, the x direction, we've got xt, which is squared. And so what sort of comes out of following this approach of trying to explain the way an electromagnetic wave or disturbance propagates is that it's the z component is going to dominate at large distances. This is dropping off by the square of the distance. This is dropping off inversely proportional. And so for me, the penny dropped. This is where the transverse wave comes from here. Purcell and Morin realize, I think, that a lot of people are going to be surprised by this result. And so they say, where is the inverse square law? Well, it's in the energy, which is the squared of the electric field. And that's the result that Lamore was particularly interested in, how much energy is dissipated by an electron orbiting an atom. So that's pretty much an outline of Lamore's formulation and the important the parts that I think are important. So going back to my original challenge to myself, is there a way to explain how electromagnetic waves leap off a wire to advanced high school at the advanced high school maths level? And I think the answer is yes, because even though I haven't gone through the equations in detail, you should be able to see that it's just algebra, really, and the students need to be able to cope with square roots and powers, squares and cubes, and I think there's enough there for the high school student who's doing year 11 and 12 maths to actually be able to follow such an explanation. The hardest bit is really there's some essential elements of special relativity you need to be able to convey, and there'd be quite a few lessons involved in getting students to follow the bits of relativity that are needed. But even then, such an explanation doesn't need, I think, a very complex view of special relativity. I think even that's accessible to students. Would Are we able to use this for amateur radio? And I think that's the challenge for amateur radio clubs that teach this stuff, particularly at the advanced level of the amateur radio license system. And I think in terms of this being used in schools, it's probably something of interest for a teacher developing a curriculum for the education system. So it's a way of teaching physics with a particular focus that you may not use in physics, the conventional way of teaching physics itself at the high school level. In terms of this presentation, what does this all imply? And I think For the non-advanced amateur operator, the qualitative analogies are still important. I think that's the best level of explanation for someone that hasn't got the advanced level of mathematics. For those that progress into tertiary studies, yep, we stick with Maxwell's equations. After all, that's where Lamore got his equation from. But I think there's a bridge between these two levels of explanations. A derivation of Lamore's formula, what it actually offers is the simplest scenario that generates an electromagnetic wave, and it helps people understand better where the transverse waves come from. And it would give amateur radio operators a bit more knowledge to be able to do a better job of doing their EMR audits for ACMA. Now, as I mentioned at the start, I haven't mentioned the magnetic field, and that's important. I think that's a challenge that's still out there. There's another article that needs to be written. If somebody else wants to embrace that, it's certainly something I'll be thinking about into the future. Will the amateur radio community update the textbooks? Well, I hope so, but it's a big ask for our mathematics averse society, and that's a significant undertaking that's there for the future. So that's all. That's my outline of can we explain EM radiation without Maxwell's equations? So back to you, Les.
Yeah. Well, thanks, George. I think you've done an excellent uh, description of what is a difficult subject, and I can certainly agree that the article by Purcell and Morin is definitely worth reading, and you can definitely download it off the internet. So we've made good time, George. So we're now
That's good.
open it up for questions. We've got one on the chat from Naratam. He's asking George if you would be okay with making the presentation slides available.
Yeah, sure. You've got a recording, and you can have the power. Well, you've already got the PowerPoints, so
Yeah.
yep. So
Okay. Well,
yes, by all means.
thank you for that. I'll just check if there's any more questions in the. There's no more questions in the chat that I can see. So I'll open it up if anyone just wants to go ahead and ask a question of George. No questions?
Well, I hope we haven't lost. I doubt we've lost the listeners, but
I think you've given them a lot to think about, George.
yeah, I sort of worry about my concern about the IEEE audience is, academics and all that may say, "Oh, yeah, we know all of that." But the thing is, as an amateur radio operator, I didn't know this stuff.
Yeah.
I mentioned the inverse relationship between distance and the electric field. I first came across that actually to do with the magnetic field and it being an inverse relationship. And I was led to believe it was because you've got a cylindrical field essentially near an antenna, particularly a large antenna. And I thought that's what that was about. But when I went through this derivation, you look at it and you go, no, that's not it at all. It's actually if you're measuring the electric field, it's an inverse relationship. And I've got to say that for somebody like me, how many years have I been doing amateur radio? And to have this stuff sort of, yeah, I only discovered this 2 years ago. And I've been at it for what, 50 years, 40 something years, I don't know. And it's like, why didn't I know this? Why isn't this in any book anywhere? It's nowhere. So I'm sure it's there in the tertiary texts on electrodynamics. So I'm sort of curious as to what people that work in this field think of all this. Do they know all of this? And why don't amateur radio guys know this? It's a bit of a mystery. So I
Well,
guess
thank you
it's more
too.
a question to the audience.
Yeah. I think the two references that you've given, Purcell are in the textbook, but also your two-part article in the Amateur Radio magazine that people can access, you know, is also, very worthwhile looking at.
Thanks.
So, has anyone out there got a question?
Yeah,
Akbar, go ahead, Akbar.
George, very nice presentation. Yeah, you're right. We as academics, we normally rely on the Maxwell's equations for our analysis of the field. I was just wondering, George, like if you have done some verification studies of comparing the theoretical models with any simulation softwares already available in the market.
Uh, yeah, I have played with NZEC. I think it's called. The amateur radio community use that. It's mostly focused uh, on wire antennas, and my particular concern more recently has been dish antennas. And I found with I've played around with ChatGPT, and ChatGPT was able to take me through the Bessel equations to solve the uh, the equations for the aperture antennas. So I found that sort of useful, and that was eye-opening as well. That a dish antenna is an aperture. I didn't know that either. And most of the literature, the amateur radio literature, they sort of talk about diffraction
Yeah.
causing the lobes, but they don't explain how that comes about. And it's to most amateur radio operators, that stuff looks like magic, you know. Mostly because, I mean, I sort of spotted it because I was doing a drift scan using that dish that is in the background here, and uh, and I noticed it was the same pattern as single slit diffraction. That's what got me thinking. But when you look in the amateur radio texts, they give polar plots, which of course you wouldn't connect to what you did in undergrad uni, you know. But yeah, I have done a bit of experimenting, mostly doing the drift scans. Yeah.
Thank you, George. Thank you.
Anyone else got a question? Just no, last chance. Well, George, I think you've given everyone, a lot to think about. Would you please join with me to thank George for a very interesting presentation and things that we need to think about. We're
Thanks, Les.
glad.
Thanks for the invitation. It was an honour to. I do feel honoured asked to present to such an esteemed audience. So thank you very much.
We appreciate it, George. Thanks. For the next event that we've got planned, members and people can check the IEEE Victoria website and the weekly newsletter, which advertises events of all the chapters. So thanks again to George as our presenter and to all of you participants for taking the time to tune in. So we'll sign off now, and thanks to everyone.
Thank you.